We build applications that must process very high numbers of events with minimum latency. Generating unique IDs for these events using the traditional method of UUIDs introduces an unacceptable time overhead into our applications, so an alternative approach is needed. I recently wrote an article on how timestamps can be used as unique identifiers, as they are much cheaper to generate than other methods of generating unique identifiers, taking a fraction of a microsecond. However, providing the same guarantee in a distributed application where functionality is spread over multiple systems, each with its own clock, can be much harder. This article describes an extension of the previously described algorithm that generates unique identifiers in a distributed environment and presents them in a format that is easy to read. This makes it easy to identify when looking at the generated identifier. We can therefore produce identifiers that are guaranteed unique across up to 100 machines. With this change, the resolution of the timestamp is now 1/10 of a microsecond, hundreds of nanoseconds. This apparent loss of precision is not important, since it corresponds to the limit of the available wall clock in many systems. Currently, we assume up to 100 hosts. Of course, Java application components run in a JVM, and there may be multiple JVMs active on the same physical machine. Speeding up generation with a saved host identifier, having a pre-configured host identifier, and keeping track of the most recent identifier in shared memory allows fast concurrent generation of timestamp-based identifiers across machines. Implementation: the happy path is simple. Take the current time, remove the lower 2 digits, and add the host ID. The value of host_IDs is hard-coded to 100, as we assume 2 digits for the host ID. As long as the generated identifier is higher than the last one generated, it's okay. Should the machine fail and the information as to the last identifier be lost, the assumption is that the time taken to restart the service is enough time to ensure there is no overlap. If the service fails, but not the machine, the information is retained. Note, this used the mapped file in shared memory supported by Chronicle Bytes, which is open source. This loop looks for the next possible timestamp, with the host ID, and attempts to update it. Using JMH to benchmark the timestamp provider with JMH. Benchmarking this utility in a single-threaded manner is pretty easy. After less than 5 minutes, we get the following result on a Windows laptop. You can get better results on a high-end server or desktop. The average time is around 37.4 nanoseconds. Disadvantages of this approach: traditionally, Java applications used UUIDs as unique identifiers. This approach is considerably more efficient than the generation of UUIDs. However, there may still be some cases where UUIDs present a more suitable approach, support is built in, and the extra overhead may not be a concern. No configuration is required. UUIDs are not predictable, the timestamp-based ones are highly predictable. Conclusion: this article has described a highly efficient approach to generating an 8-byte lightweight identifier that is unique across many hosts, based on some predetermined partitioning by host identifier. The identifier is still easily readable as text in a slightly modified form of a timestamp. Thanks for watching. Please subscribe.